Morning, grade 10s. Welcome to our distance learning. Hope everyone's staying safe and well at home. What we're going to be going through today is one of our first lessons that you're going to be covering while we are not at school. I have posted office hours on Google Classroom that you'll be able to see. That's the easiest time to get a quick response from me during that time. I am going to be checking Google Classroom and my email throughout the day though. It's just outside of those office hours, the response may be a little bit slower. I've also posted a Google form just for you to fill out at the beginning of the week to check in with you and how you're doing and making sure that you can access everything that you're going to need over the next few weeks. And again, feel free to email me or post on Google Classroom if you're having trouble accessing anything. So we'll be following along with the lessons, and these videos may help you understand exactly what we need to get through. So first thing that we're going to go through today is talk a little bit about Canadian weather. This is in 7.1 and 7.2 of your textbook, like you can see, page 260 to 262, 269, and 279 to 285. All right. So what we're going to be going through today is we're going to be talking about heat transfer, the difference between weather and climate, and then we're going to talk about a few things that can actually impact our local climate and weather, including our atmosphere, the oceans, and land. Last, we're going to summarize a little bit about our local climate here in GTA, and then talk a little bit about how Toronto's climate has changed over time in an investigation you're going to be doing after the slides today. Okay, so let's get started. By the end of the class, what you should be able to do is by the end of this video and the end of the activity for this first hour that we have slotted for you is you should be able to compare and contrast how heat can be transferred, compare and contrast the terms climate and weather, as well as identify factors which can affect climate. So we're going to start off talking about heat transfer. So there's different ways that heat or energy can be transferred from one place to another. The first one is through something called convection. So convection is the transfer of thermal energy through the movement of particles. So this could be things like gases or liquids. If you've ever used, say, a space heater before, you're heating yourself or the room by convection. So the warm particles of gas that are coming from the space heater is what's actually heating your room. Okay, so that would be convection. You may also have at home a convection oven. The difference between a regular oven and a convection oven is not only is the heat being given off by the sort of coils at the bottom of the oven, it's also got a fan in it, so there's air moving throughout the oven, so extra energy is being transferred also through the movement of those gas particles. So that is convection. Second type is conduction. Now, conduction is a transfer of energy through direct contact. So the difference between, say, the inside of your oven, if you have a convection oven, and the top, sort of the elements on your stove, this would be through direct contact. So that would be conduction, not convection. Conduction is when they're in direct contact with one another. So when I put a pot of water onto the stove directly on those elements, okay, that is a transfer of energy through direct contact, so that would be conduction versus convection. A little bit different than warm air blowing on you from a space heater. Okay. The last type of heat transfer is radiation. Okay, so that's the transfer or emission of energy as waves. Okay, so the best example we have for that is the sun. So we're not in direct contact with the sun. There's not gases coming from the sun coming towards us that are heating us up. How we're actually getting that heat from the sun is through energy being sent by waves. So things like we all know we need UV protection. That's a type of energy wave coming from the sun, comes towards us, and that energy then can heat up our planet. So we're not in direct contact with it. We're not in contact with particles from it, but we're getting heated by it through energy being sent to us through waves. Okay, so if you're getting heated or energy transferred through the movement of particles, it's convection. If it's being through direct contact, that would be conduction. And if it's through the transfer of energy as waves, that would be radiation. So those are the three main ways heat can be transferred from one place to another. Another thing that we just have to clarify is two terms that are often used interchangeably in common language, but scientifically actually mean two very different things. And that's climate versus weather. So they are very closely related to one another, but they are in fact different. Okay, we're going to talk about the differences. There's also a really good video. It will be linked right in this graphic here on your slides. It's also hyperlinked on the end of this first module sort of instructions on Google Classroom. The video is actually just called Climate versus Weather. You can click there and watch this video if my explanation doesn't really make sense. So first one we're going to talk about is climate. Climate is the average weather conditions that occur in a region over a long period of time. Okay, so just like you have an average mark in the class, and that may not represent the mark that you got in each individual assignment, climate is sort of our average expectations of what the conditions will be outside based on usually about 30 years of data at least. Okay, so the fact that we expect snow in the winter in Canada is part of Canadian climate. The fact that we expect it to get a lot warmer in the summer here in Canada, that would be part of Canadian climate. Okay, so it's expectations of what the conditions will be outside over a long period of time, or over a long period of time of collecting data. Okay, so it's what we expect to get. Okay, this can be affected by a lot of things like the latitude, where you are on the planet, altitude, how high you are, the geography and the topography, and we're going to explore in just a few minutes some of the things that can impact climate in just a few slides. Weather is a little bit different. Weather is the specific environmental conditions that occur at a particular place at a particular time. So if I describe to you that if I look out my window right now, I can see that it's pretty cloudy, it's a little bit cool, that's me telling you the weather that's occurring outside. Now, I'm going to have a certain expectation of what the weather is going to be like in April in Canada. That's our climate. Okay, we know that in April we probably expect it to be a little cool, a little less snow. It's not going to be super super warm, but not super super cold. That's the expectation of Canadian climate in April. But what we actually get today is our weather conditions. So it's the specific data points from that day. Okay. So you may hear on the news about the temperature, the air pressure, the cloud cover, the precipitation for that day, and that's weather versus climate. Okay. So things like how much wind there is, the atmospheric pressure, the temperature, the clouds, the humidity, the precipitation of that day is weather, and how much wind or pressure or the temperature we may expect based on at least 30 years of data would be the climate. Okay, so it's expectations versus what you actually get. Okay, so there's a few things that can impact climate that we're going to talk about, and I'll just move myself out of the way. The first thing we're going to talk about is the sun. Okay, so both weather and climate depend a lot on how much energy is given to a specific region. So almost all energy on Earth really originally comes from solar radiation from the sun, or that energy that's coming to us from the sun from those waves, okay, those energy waves. Essentially, the more solar radiation we get, the more energy we get from the sun, the warmer we would expect the climate and the weather to be, because that radiation is going to be converted into heat. Okay, so places like the equator, where they get lots and lots and lots of solar radiation, we would expect, and we see very often, warmer climate and warmer weather patterns because they get that extra energy from the sun. Somewhere like in the north, where it's a little bit colder, where they get less solar radiation, so like in northern Canada, we see colder weather and climate patterns because they get less energy from the sun, so it's going to be cooler. It's not going to be quite as hot. Okay, this measure, the amount of solar radiation that we get, is called insolation, and we measure the insolation. That's essentially saying the more you have, the more insolation you have, the more solar energy you're getting from the sun, okay, or the more solar radiation you're getting. So it's just the total amount of solar radiation received on a given surface during a given time. It's called that. Like we said often throughout this year, scientists were not super creative when we name things. It comes from the Latin word insolare, which just means to be exposed to the sun. So somewhere like Canada, we're going to have less insolation, less solar radiation than somewhere like, I don't know, Cuba, where it's hotter. Okay, they're closer to the equator, they get more solar radiation, more insolation, so their climate and their weather is warmer. Okay, the next thing that we're going to talk about that can affect climate is the atmosphere. So what we need to know is that there's continuous currents of air or movement of air between the poles and the equator, and that can affect the local air pressure and wind patterns. So air closer to the equator, because it gets more exposure to solar radiation, it has more insulation, is going to heat up. If you remember from grade 9 when we learned about the particle theory of matter, we know that when particles are hot, okay, they're going to move around more quickly, they're going to bounce off each other more, so they're going to separate from each other more, which means they get less dense. Less dense things, we also know, float. So really hot areas near the equator, it's going to have air that rises and becomes less dense and eventually cools down. On the other hand, near the poles, okay, where it's really, really cold, there's less solar radiation, less insulation, that gas is going to cool down, the particles are going to move less quickly, they're going to get closer together, they're going to become more dense, and they're going to sink. So what we see is these patterns of these bubbles of heating air rising up and cooled air falling down. Heated air rising up, cooling air falling down, okay? And those cyclical patterns of warm air rising and cool air falling is going to affect, like we said, the air pressure, and also will cause different wind patterns to occur. These movements or currents that move away from the equator and back towards the poles are consistent. We see these patterns often, and it can be caused by something also called the Coriolis effect. Okay, so Coriolis effect, it's a fancy physics term, so don't worry too much about it, but it's just the deflection of any object from a straight line when it's spinning. So essentially what it's saying is not only are these sort of pockets of warm air and cool air rising and falling, rising and falling, rising and falling, because the Earth is also spinning, they're also kind of twisting on its side as well. So that's where we get, for example, the northeast trade winds, because of this pattern of warming and cooling air with the spinning of the Earth kind of twisting it on its side. Okay. So a big thing is we know that the sun and the amount of solar radiation can impact how gases are moving, which can impact pressure and wind patterns. The third thing we're going to talk about are our oceans. Okay, so ocean currents are the main pathway for the transfer of thermal energy. So global winds will push water on the surface, and it will create these consistent patterns that we see that we also call currents, like the air currents. So we'll see sort of these cycles of water that continue to kind of spin around or move around in consistent patterns. This can be caused by the Coriolis effect. The spinning of the Earth can cause some of the water to move. Also, the winds, like we said, can cause water to move. But for example, when warm water near the equator, so we know this water is going to be warmer because it's getting more solar radiation, more because of the greater insulation on the surface of the water there. It's going to move around and it's going to warm these areas. Okay, so warm water is going to be received by these areas. So that may warm that climate slightly. Whereas the colder water from up north, where it's got less solar radiation, so less heat, so the water is cooler, it's going to come down, and that's why we see things like on the west coast of Canada, a little bit of a cooler climate, because the water that's coming near to it is cooler. Okay. Not only that, but also just proximity to large bodies of water can really impact your seasonal temperatures. In general, what we see is areas that are really close to large bodies of water tend to have more moderate climates. And what that means is they don't get as cold in the winter, but they don't get as hot in the summer. It's more consistent versus getting really hot summers and really cold winters. This is because water has a property, it's got a very high specific heat capacity. It's a fancy chemistry way of saying water takes a really long time to heat up. You've probably all seen that before. If you put a pot of water on the stove to try to cook, it seems like it takes forever for a pot of water to boil, but it also takes a really long time for water to cool down. So that can impact the climate of cities or areas that are really close to large bodies of water. So let's look at an example. We have an example here of two cities, okay, one in China, one in Chile. And we can see their average temperatures are both very close. So the average temperature here is 11 degrees, whereas the average temperature here is 12 degrees. So the expectation is that those climates are very similar. The difference is, in China, this is a landlocked area, so it's not very close to a large body of water, whereas this city in Chile is very close to a large body of water. So what we see, even though their average annual temperatures are the same, the degree to which they change is much different. So an area that's far away from a large body of water, we see in the winter it's pretty cold, and in the summer it's pretty hot. So we're going from -4 degrees to 26 degrees Celsius. So the amount that that temperature ranges is by 30 degrees. Okay, so really cold in the winter, hot in the summer. On the other hand, this city in Chile, because it's very close to a large body of water, in the winter it doesn't get as cold because heat is trapped in that large body of water and is slowly released over the winter time. Okay, so we see that over time that temperature is moderated a little bit, or it doesn't get quite as cold because there's heat consistently being released throughout the long winter from that large body of water. So it gets cold, but not quite as cold. Same thing in the summer. Once that water finally cools off and then we enter summer again, what we see is the summer doesn't get quite as hot because that large body of water is going to absorb a lot of that heat from solar radiation over the summer. So it gets warm, but not as warm. So even though the average annual temperatures are the same, we see the range is a lot less. So this climate in Chile, we would say, is a lot more moderate. So it doesn't have as extreme of a change like in China because of its proximity to a very large body of water. Okay, so the large body of water keeps the climate warmer in the winter and cooler in the summer. Okay, we're also going to talk about the configuration of land. So how the land is actually built, okay, or what it appears to be like, will also affect climate. Okay, the Earth's surface and density can produce friction. So if it's a really rocky, bumpy climate, it's going to be more difficult for the wind to move across it quickly. So that's going to slow global winds in that area. Also, the coloring of the land can affect it. So dark colors tend to absorb heat and make things hotter, whereas light colors tend to reflect heat and make things cooler. That's why a lot of times in the summer, people like to wear like light colored t-shirts because you can stay a little bit cooler in them. So it's places like up north where the land is covered in snow and it's a very light color, it's going to reflect even more of the heat, okay, and make it even colder because the heat or energy is going to get reflected back into the atmosphere. Whereas maybe somewhere like a city, a downtown area with lots of black streets and black parking lots and black buildings, we may see that climate or weather pattern over time expected to be warmer because all those dark colors are absorbing the heat and then making it even hotter. Now, in the GTA in Canada, we have a few expectations of our climate. So we live in the temperate deciduous forest biome here where we are in the GTA. So you may remember learning about those biomes back in grade 9. We have an average annual temperature between 10 and 15 degrees Celsius. We expect somewhere between 750 and 1500 millimeters of precipitation a year. We have very well defined seasons. We know our expectation of climate in the summer is a lot different than our expectation of climate in the winter. Not everywhere in the world has such defined seasons. And common plants that we see based on our climate would be things like deciduous trees, shrubs, grasses, ferns, and flowering plants. So you're going to do a little bit more of an investigation now into Toronto's climate and how it's changed over time. So this is an activity you can find on page 270 of your book. Okay, and we're going to ask you to complete activity C4 on page 271. So it looks like this: C4 inquiry activity continue. There's some information and instructions on page 270. But what you're going to be doing is either using some graph paper or you can use Google Sheets like we've been using throughout this year. You're going to be tracking some data about Toronto's climate and making some conclusions about some of the things that may have impacted our climate and weather in Toronto over time. Okay, so there is instructions in your book on page 270 and 271. So read through those pages. If you have any questions, send me an email. And there's also additional instructions on how to submit it on your outline for this week that you can also find on Google Classroom. Okay. So I hope this helped Canadian weather lesson make a little more sense. And again, reminder, check my office hours out for this week if you need any extra help or quick answers to questions, I'm always available by email and Google Classroom. I'll try to check it as often as I can. And just encourage everyone, stay home, stay safe, and hopefully we'll be back together soon. Okay. Thanks. See you guys soon.